Hey guys, today I'll be going through the implementation of DCGAN or Deep Convolutional Generative Adversarial Network on the famous CELEB-A dataset. And before we start, a quick word. If you have not already done so, please go ahead and hit the subscribe button. And if you happen to like the video at the end of it, do not forget to hit the like button. All right, let's get started. So this is our CELEB-A dataset. It's a very famous one for computer vision. And what this dataset contains, it is a large-scale face attributes dataset with more than 200K celebrity images, each with 40 attribute annotations. The image in this dataset cover large pose variations and background clutter. CELEB-A has large diversities, large quantities, and rich annotations, including 10,177 number of identities, and images are 202,599, 5 landmark locations, and 40 binary attributes annotations per image. Okay, and what is facial attributes prediction actually? So FAP or facial attribute prediction is a computer vision task about deducing the set of attributes belonging to a face. Examples attributes are color of the hair, a hairstyle, age, gender, etc. And facial attribute analysis has received considerable attention when deep learning technique made remarkable breakthroughs in this field over the past few years. And deep learning based facial attribute analysis consists of two basic sub-issues. One is facial attribute estimation, FAE, which recognizes whether facial attributes are present in a given image. And the number two is facial attribute manipulation, or FAM, which synthesizes or removes desired facial attributes. Now in this video, I will be implementing GAN to produce images from the original CELEB-A dataset. So let's quickly take a look at the fundamentals of GAN. So this is how GAN works. We have two basic fundamental blocks of GAN, which one is generator and the second one is discriminator. The generator generates new data instances that are similar to the training data, in our case CELEB-A images. Generator takes random latent vector and output a fake image of the same size as our reshaped CELEB-A images. And the discriminator is like the detective in this whole process. So the discriminator evaluates the authenticity of provided images. It classifies the images from the generator and the original image. Discriminator takes true or fake images and output the probability estimate ranging between 0 and 1. So very much what the discriminator does is it takes each image and tells it whether it's fake, that is 0, or it's a real image, that is 1. And this is a loss function of the GAN framework. It's a min-max kind of algorithm, and here D refers to the discriminator network, while G obviously refers to the generator. Okay. As the formula here shows, the generator optimizes for maximally confusing the discriminator by trying to make it output high probabilities for fake data samples. On the contrary, the discriminator tries to become better at distinguishing samples coming from G from samples coming from the real distribution. The GAN training process consists of a two-player mini-max game in which D is adapted to minimize the discrimination error between real and generated samples, and G is adapted to maximize the probability of D making a mistake. When G does a good job, to fool D, the output probability should be close to 1. Now, that's the fundamental GAN framework, but DCGAN is called deep convolutional because in DCGAN, we bring the mathematics and the architecture of convolutional layers. So quickly have a look at what's the difference between a normal neural network and a convolutional neural network. So The convolutional neural network is a subclass of a neural network which have at least one convolution layer. They are great for capturing local information, for example, a neighbor pixel in an image or surrounding words in a text, as well as reducing the complexity of the model for faster training. And CNN also needs fewer samples and reduces the chances of overfitting. A CNN is a neural network where one or more of the layer employs a convolution as the function applied to the output of the previous layer. CNN does convolution between the previous layer's output and the current layer's kernel. This is a kernel in this image, the small matrix. And if the window is greater than size 1 into 1, the output will be necessarily smaller than the input unless the input is artificially padded with zeros. And hence CNNs often have a distinctive funnel shape. That is, the input is larger matrix. After applying the kernel, we have a smaller matrix. And this is just the weighted sum between the kernel weights and the input values. So this is a subject by itself, and I can make a separate video altogether on the fundamentals of CNN, which I will actually do after a while. So in this one, I'm not going in more detail of the CNN. So let's quickly look at the DCGAN, that is a deep convolutional GAN on GAN models architecture. So DCGAN was introduced pretty recently, and it involves convolutions to the generator and the discriminator network. However, this was not simply a matter of adding convolution layers to the model, since training became even more unstable. Remember, GAN by itself was extremely sensitive to parameters, and DCGAN is even more so. So several tricks had to be applied to make DCGAN useful and stabilized. And these are those four things that were four guidances that were mentioned in the original research paper. One is batch normalization was applied to both the generator and the discriminator network. Then dropout is used as a regularization technique. The generator needed a way to upsample the random input vector to an output image. Transposing convolutional layers is employed here, and leaky ReLU and TAN-H activations are used throughout both networks. So this is again the architecture of a convnet or CNN, and this is the starting point is the input image or the input matrix here. So unlike a regular feed-forward neural network whose neurons are arranged in flat, fully connected layers, layers in a convnet are arranged in 3 dimensions: width, height, and the depth. So CNNs or convolutional neural network are networks with architectural constraints to reduce computational complexity and ensure translational invariance. And what is translational invariance? So it means that the network interprets input patterns the same regardless of translation in terms of image recognition. So a banana is a banana regardless of where it is in the image. And finally, this is the architecture of a DCGAN. So now first, let's understand how traditional image processing works. So traditionally, convnet uses a network that takes an image with the dimensions height, width, and number of color channels as input, and through a series of convolution layers outputs a single vector of class scores with the dimension of 1 into n, where n is a number of class labels. In DCGAN, however, under the generator part, to generate an image by using the convnet architecture, we reverse the process. Instead of taking an image and processing it into a vector, we take a vector and upsize it to an image. That's what this part is doing. So overall, the core of DCGAN architecture uses a standard CNN architecture on the discriminative part of the model. But for the generator, convolutions are replaced with up convolutions. So the representation at each layer of the generator is actually successively larger, as it maps from a low dimensional latent vector onto a high dimensional image. It needs a layer to translate from coarse salient features to a more dense and detailed output. Now, let's quickly go through the original paper that was published in Jan 2016 by Alec Radford and Luke Mades and Sumit Chintala. So, the original paper mentioned few things to stabilize GAN, like I discussed earlier, that GAN by itself is super sensitive to parameters, and DCGAN is even more so. So the architecture guideline that they have given for a stable DCGAN are the following: replace any pooling layers with strided convolutions or discriminator and fractional strided convolutions or generator. Use batch norm in both the generator and the discriminator. Remove fully connected hidden layers for deeper architectures. Use ReLU activation in generator for all layers except for the output, which uses tan H. Use leaky ReLU activation in the discriminator for all layers. So you will see that we will implement these things in the model that I'm going to start coding now with a CELEB-A dataset. Further, this image, you already saw it, that it takes, so what they say is that a 100-dimensional uniform distribution Z is projected to a small spatial extent convolutional representation with many feature maps. So this is a 100-dimensional vector at the start, and this is a whole generator part. A series of 4 fractionally strided convolutions. In some recent papers, these were wrongly called deconvolutions. Okay, forget it. A series of only 4 fractionally strided convolution, then convert this high-level representation into a 64 into 64 pixel image. Notably, no fully connected or pooling layers are used. So basically, what the generator takes in some noise, the 100-dimensional vector here. Then it uses conv transpose 2D, which is essentially kind of the opposite of conv layer. So it upscales the image to 1024 channels and then 4x4. We can see that depth and height is 4x4. Then it upscales again to 512 channels with 8x8. And then it upscales to, and then the whole process goes on. The next upscaling is to 256, 16x16, till finally we reach the last layer, which is 64x64, and then by three RGB layers, RGB channels, sorry. Okay, so this is the overall architecture of the generator. I strongly suggest that you should go through the paper once. It's a wonderful paper to read, indeed. All right, now I am going to start with actual coding. And for the data part, I was actually using these kaggle competition. It was not really a competition as such. So this dataset was uploaded to Kaggle 3 years back. It's a very famous and very well-known dataset, CELEB-A faces, that we already discussed, and they actually mention the details of the dataset here and what's the task to be completed for this challenge. And so I downloaded the whole dataset first to my Google Colab. I will come to that in a second. And these are the dataset this folder has all the images of 200,000 plus .jpg files, and these are some CSV with the labeling of the images. So here I am in my Google Colab, the start of the whole code, and in this cell, what I'm doing is connecting my Google Drive with Kaggle dataset. So basically, I'm bringing in this whole Kaggle data, 1.4 GB, I guess, yes, 1.45 GB, to my Google Drive, so that I can use the Google Drive data inside Kaggle. So this code is pretty boilerplate. You can find it all across the web, and in the documentation very well explained. So the first line here is just bringing in the google.colab and import drive, and then I'm mounting the Google Drive, and then this particular line pip install Kaggle. This is a Kaggle package, and you may not have to install it, but I had to force reinstall it because the Kaggle package that Colab had in my case was slightly outdated, and I was getting some warnings and few errors as well. So I had to completely do a fresh reinstall of Kaggle. and then I have to also specify the os.environment. This is the folder contain the drive the contain drive my drive kaggle dataset. This is where the API or the .json file resides that you get from kaggle. The detail, I'm not going to the details here in this video because there's a lot of videos on these and how to connect kaggle data with Google Drive and Colab. So this is a standard code, and then you have to change directory to the Google Drive through this line os.chdr, because uh, unless you change directory, you if you after you get the data in Google Drive and start coding immediately or unzip the data, then all unzipping will be done in the virtual machine of Colab. So take a look at this next line so that you will understand that why I need this line. Here in this line, Kaggle dataset download. Again, it's a standard line you will get from Kaggle page itself to download the data from Kaggle to Google Drive, and then you have to unzip the data. So this unzipping part, I have to change the code here. I think I have taken it from my earlier project on gravitational wave detection. So it will go something like so it will go something like my drive, CELEB dataset, and the dataset zip. I think the folder will be, the whole data will be downloaded as a zip file. So unzipping this, before unzipping this, you have to do a os.change directory here. Otherwise, the whole unzipping of this data will be done in the virtual machine of Colab, that is in this folder. This is the folder structure, directory structure of Colab's virtual machines, and it will be there only for this particular session, that is 12 hours or 24 hours, depending on whether you have the free version of Colab or the pro version. So if I do os.chdr, then all the next operation will be executed in that particular directory, and that's what I'm changing my directory to Google Drive, and then my unzipping command will unzip this whole .zip folder into Google Drive. Okay, so that was the first cell, and then my next is the standard importing of all the libraries. It's just the standard libraries, NumPy, Pandas, and etc. The important part is the Keras. I'll be using TensorFlow and Keras here. So I'm importing all the Keras.layers, conf2d, dropout, dense, flatten, conf2d transpose, batch, normalization, leaky relu, and reshape. All right, now I am going back to VS Code because it's slightly easier for me to write codes in an IDE compared to Colab. Okay, so first I'm just creating an empty array, and that array will contain the full image path of each of the .jpg files. Full image path. Full image train path. So first get the folder name which contains all my images, and that's this folder actually. I'm just following the folder structure in a Kaggle challenge, so it's up to you how if you are working in a local machine or in Colab. Certainly this will be difficult based on where you keep your .jpg files. And now I will be looping over each of the .jpg files and creating a full path of the JPG files and adding those paths to this array, so that this array contains the full path of each of the .jpg files, and from here I can extract how many ever image files I want to extract. Because remember, this for this training I will not be using the 200,000 files because that's too many for both my local machine and even for Google Colab Pro. I was getting indeed out of memory error multiple times when trying to work with the full 200,000 images. So I will be extracting only 50,000 and work with that. and then let's see how it goes. Okay. In os.listed full image train path. I'm looping over all the file names, and if the file contains .jpg, if jpg, okay. Remember our file structure in Kaggle. So let's quickly have a look at that. So this is our file structure in the original Kaggle dataset. So the root folder contains an folder named img align celeb-A that has another folder with the same name, and within that I have all the .jpg files of 200, 2000, and 569, 570 indeed. Okay, so oh no, this will be a few more because I have probably 20 or 30 images here. So anyway, this is our folder structure. So let's loop over that. If .jpg in file, I'm just adding, and now I'll be building a image path containing this full thing plus the .jpg file name. All image path .jpg and full image training path. And now I'll be extracting 50,000 images from these array, all image path. So let's name a variable. Equal to with the slice notation. Let's check out if they contain the correct size. Image just print the lane of it. Yeah, it printed 50,000. Okay, now this is my overall plan to work with the 50,000, but during the actual coding part, because I have to run each cell immediately and don't wait for the result, I don't want to wait to loop through the 50,000 images for each cell. I will just take 500 so that all my different cells in this Jupyter notebook runs quickly. And now I will be working with the image. So let's add code. So first I will do is I will crop the images so that I get only the portion which contains a face. So I'll be making use of this Python image library PIL and the image module, which has a crop function. Let's do that. First, I'm defining a cropping box that is, which is a tuple containing 4 numbers, and this defines pretty much the left, the left side, upper side, right, and lower side of the cropping parameters. Cropping box. I checked this number; it kind of worked well for me. 175, and now I have to actually crop them. So this. So this is my this variable training images will contain my full image array, that is the full numpy array of the images with which I will be training. So that's what I'll be building now. And I will be making use of, I'll be first reading the image token. Cropping box. my np.array image. Okay, makes sense. I'll be resizing them to 64 by 64 size. Resize text. Quickly check their documentation. Resize text size as a tuple int resample. Okay, size is enough for me. 64 by 64. And for path in image 50K, this should work. Let's quickly check out lane running images. NP not defined. That's strange. Okay, I did not run the whole file indeed. Let's let's comment this out because I don't need them here in my local environment. Okay. Now, yeah, it worked. So my training images now has 500 rows. Remember, we selected only 500. Later, of course, like I said, I will be changing it to 50,000. Now, let's quickly check if my training image is actually what they are. This should be NumPy array. So, oops, sorry. Training, I'll print training images. And yes, they are three-dimensional NumPy array like this. So yeah, it goes on for 500 rows. That is for 500 images. Yeah, so as you can see, the number varies widely: 10, 15, 17, 189, 194, 234. We cannot have that. I will have to normalize it to make it between, to limit it between 0 to 1. So let's do that first. Clear cell output. I will be manually normalizing it. I remember the concept of normalization. That is right now my numbers, all these NP array ranges between 0 to 255, which is 255 being the maximum value. And I want to normalize these image values to between 0 and 1. And that's because neural network process inputs using small weight values, and input with large integer values can disrupt or slow down the learning process. As such, it is a good practice to normalize the pixel value so that each pixel value has a value between 0 and 1. So, and our normalization formula is this. Normalized is between, it is a min max normalization, so minus mean x divided by max x minus mean x. The whole thing is again between my braces. And yeah, now this is what I am going to implement for my NumPy array representing the full image set. So I in range training images. So I am looping over my full training image. This is the array containing all the images. I'm looping over each of the element over for it. So each training image will be denoted by training images I. And that value should be, let's do Sorry. No, I do need the training images I minus training training images I, the mean value, and that needs to be divided by this part, max minus mean. And remember, for our case, the max value of the pixel is 255. So we can actually replace the max value with 255. That's the max value for each pixel. 255 minus training images I, the mean. Okay, that should work. And now let's convert this whole thing to proper NumPy array. Training images equal to training images. This will give me a well-structured NumPy array with which I can work. And now quickly print them to check if they were really converted between 0 and 1 value. Running images. Yes, indeed. Now you can see that all values are between 0 and 1. All values, and we can actually check even further that all these values, the mean and maximum values of these this is a 4-dimensional NumPy array, so we can actually check that none of the values are beyond 0 or beyond 1 on the minimum side or maximum side respective value. Let's quickly do that. So I have to print the max values of these training images columns. So I'll be using np.max, and I'll be np.max. What kind of arguments I take? Let's see the definition. Yeah, it takes print. Oh no, 1 second. Okay, forget about it. np.max takes actually the first argument is the original NumPy array, and it takes an axis parameter which will be 0. And similarly, I want to do that for the minimum values in n. Now let's print it. Yes. So okay, let's just quickly check it as it is. So first I printed the max values of these training images, which is a 4-dimensional array. So these will print the maximum column values, and we can see that none of them goes beyond 1. Okay, and we also printed the minimum values for x is equal to 0, and we see that all of them are capped at 0. So no minimum values which goes beyond 0. That's what we want. Okay, so our normalization is done. Let's comment that out. And to check the shape of the training images, I can quickly print that shape. And that's 500 number of rows or samples. And these 3 terms are actually the shape of the image. Remember, we resized the images here, resize 64. So here I have an image size of 64 by 64, and 3 are the number of channels. So all right, now I want to print the actual real images, few of them. I want to print 10 actual real images, so that I will do it from here. So this is the code to print the images. I have a plot figure size declared here, And now I'm just looping over a range of two. That is, I want to print two rows of images, and in each row there will be 5 images. So the inner loop has will range over 5, and then I'm using the IM show and PLT tight layout. The tight layout documentation says, oops. Anyway, the documentation is not coming here. Okay, I'm just running this cell, and I get a, yes, so I get a plot of 10 images. These are actual images from the real data of CELEB-A. All right, now my next step is to actually build the generator function, and that would be, I'm not typing the code here because that will make the video length incredibly long. So it's better for your time as well. So this is my code for the generator part of the model. Now I will go over the explanation of each of these terms and what they are doing, what is especially this topic of conv2D transpose before we go further. So initially we declared this noise shape to be 100. Remember the original, from the original paper of DCGAN, it starts from a vector of 100 at the first step. So let me just quickly open that paper. So here is the original paper of DCGAN, and this is the generator part of the model architecture. And we can see that the starting point is a 100-dimensional or a vector of 100 dimension called Z, and it clearly says that a 100-dimensional uniform distribution Z is projected to a small spatial extent convolutional representation with many feature maps. Yeah, so that's what we are doing here. Let me go to my code. That's what I'm doing here. That this noise is that randomly generated starting point, or Z, as per the architecture. And the first layer is a dense layer, and then I am reshaping it to 4 by 4 by 512. And a quick word on this input shape, which I'm giving these noise shape of 100. So if we see the documentation, so this is the documentation from Keras, and it says that note that you can also omit the input shape argument. In that case, a model doesn't have any weights until the first call to training or evaluation method. So in this case, I created a model, sequential model, and then add a layer, dense layer, and then another dense layer. But till this point, there is no weights or no input shape is defined here. That means a model.weights not created yet. So to have these weights initiated, I have to supply the input shape, and that's what the next block of code is doing. Whereas if you specify the input shape, the model gets built continuously as you are adding layers. So that's a situation definitely I want here. Okay, and so I'm then in the next one I am reshaping it to 4 by 4 by 512, and this is the most important part, conv2D transpose. So remember, the whole architecture of generator is like a opposite of normal CNN. We start from a low dimensional vector and upsample it. So that's this conv2D transpose function is doing here. So a quick look at the documentation. All right, before we go to the documentation, have a quickly check out what this conv2D transpose is doing at all. So this image, it's a normal CNN. So we start with a 3 by 3 image and apply on this image a smaller kernel or smaller matrix, also called filter. This is my 2 by 2 kernel, and the output of applying this kernel on this image is this 2 by 2 matrix. So we start with a larger matrix, apply a smaller filter on this large matrix, and output comes a smaller matrix compared to the input. But what if you want to start with a 2 by 2 output and apply a kernel and get a larger image? So that's the situation we are dealing with in generator part of a DCGAN. And it is kind of the reverse of the normal CNN, and this whole thing that we are seeing here, this problem can be solved with the conv2D transpose API of Keras. So now let's quickly go over their documentation. So this is the API Keras documentation here, and it clearly says transposed convolution layer, sometimes called deconvolution. The need for transport convolutions generally arises from the desire to use a transformation going in the opposite direction of a normal convolution, the most important part. Opposite direction of a normal convolution, and this is what we do in a generator. We start on the opposite direction of a normal CNN. That is from something that has the shape of the output of some convolution to something that has the shape of its input, while maintaining a connectivity pattern that is compatible with said convolution. All right, so this is pretty much the most important thing you have to understand. And they have, if you are interested, you can check out their source code here in the GitHub under the Keras team, Keras, and you will find this class under the layers and then convolutional.py file. And this is a beautiful piece of code, very large code base indeed. And we can see that these within the init function, they initiate all these same kind of arguments that we apply for a normal CNN: kernel size, filter, strides, padding, everything is there. All right. And similarly, so I'm adding the same kernel size, the same kind of arguments to my conv2D transpose function: kernel size of 4, strides of 2, and padding same. And remember, the conv2D transpose is fundamentally works like CNN, it just in the opposite direction. So the transpose, under the transpose layer, it simply swaps a backward and forward pass, keeping the rest of the operation the same. And that's why the transpose convolution also will take the similar kind of arguments like slide and kernel size, etc. And I found this beautiful blog. If you are interested to know more about the kernel size, strides, padding, etc., and I will put a link to this blog in the in the video. So here's the blog I was talking about. Understand transposed convolution, written by Quan Wei. It's quite a long blog and it's really exhaustive. So he has given some of the good definition. So here, what are the parameters? Kernel size, strides, and padding in Keras conv2D transpose. So kernel size in convolutions, that is in normal convolutions, the kernel size affects how many numbers in the input layer you project to form one number in the output layer. The larger the kernel size, the more numbers you use, and thus each number in the output layer is a broader representation of the input layer and carries more information from the input layer. But at the same time, using a larger kernel will give you an output with a smaller size. And this is for normal CNN, and see how this is a pictorial representation of this kernel size effect on output. But this mechanism is just the reverse for transposed convolution. That's what he's saying in his blog as well. In transposed convolution, when the kernel size gets larger, we disperse every single number from the input layer to a broader area. Therefore, the larger the kernel size, the larger the output matrix, if no padding is added. So 2 by 2 matrix, input matrix, on this we apply a 3 by 3 kernel, and I get a larger output matrix under the transposed convolution. Similar kind of cases for strides as well. So in normal convolution, the strides parameter indicates how fast the kernel moves along the rows and columns on the input layer. If a stride is 1, 1, the kernel moves 1 row, 1 column for each step. If a stride is 2, 2, the kernel moves by 2 rows and 2 columns for each step. As a result, the larger the strides, the faster you reach the end of the rows or columns, and therefore the smaller the output matrix. And this is an image of that movement, but this mechanism is same just the opposite direction for transposed convolutions. Here, the stride parameter indicates how fast the kernel moves on the output layer. As explained in the picture below, notice that the kernel always moves only one number at a time on the input layer. Thus, the larger strides, the larger the output matrix, if no padding. Okay, so these you can of course go through this blog. It's a really beautiful blog, and he explains all these parameters very well. So going back to my code, and after the conv2 2D transpose, I am adding a batch normalization. Okay, before I go to batch normalization, another quick word on this conv 2D transpose. Keras also has another function called upsampling 2D, and that's sometimes is confusing that because many people think conv 2D transpose is also effectively doing an upsampling, and the other function which is called upsampling 2D, that is also doing upsampling. So what is the difference? So remember, upsampling 2D is just a simple scaling up of the image by using nearest neighbor or bilinear upsampling. So nothing smart, no special computation is done on that. But the advantages of upsampling 2D is it is cheap computationally. On the other hand, this function, that conv 2D transpose, is a convolution operation whose kernel is learned just like normal conv 2D operation while training your model. So using conv 2D transpose will also upsample its input, but the key difference is that the model should learn what is the best upsampling for the job. So it is in a simple word, it's much more smarter way of computing compared to the other function upsampling 2D. All right, now my next one is batch normalization is added to the model after hidden layer, but before the activation. So batch normalization is pretty much to stabilize the overall training process. So batch normalization standardizes activation from a prior layer to have a zero mean and unit variance. This has the effect of stabilizing the training process. Under batch normalization, it fundamentally limits the amount by which updating the parameters in the previous layers can affect the distribution of inputs received by the current layer. These decreases any unwanted interdependence between parameters across layers, which helps speed up the network training process and increase its robustness, especially when it comes to network parameter initialization. So batch normalization is used after the activation of convolution in the discriminator model, and for the generator model it is used after transpose convolution layer, but before the activation layer, that is before applying leaky ReLU, and that's why I'm applying leaky ReLU after the batch normalization is done here. Okay, now that the generator model is done, let's quickly see how our generator model is doing in outputting some images from random noise. So I have this code here. I'm just creating a random noise of 100-dimensional vector, and then invoking or passing that noise to my generator model, and then plotting with ImShow generator image. Let's run this cell. All right, it's interesting. So this image that is created by my generator model from the 100 vector, it's just pretty much random noise, but it's the potential of the generator model is shown right here, that given just 100 vector random noise is created this image, and that exactly the job of the generator model. Okay, so now in the next model, which is discriminator, and this is my code for discriminator model. It is much more conceptually easier to understand if you understand CNN, because discriminator is just a regular CNN model implemented. So here I'm giving, again, it's a sequential model of Keras, and I'm in the first layer I'm creating a plain old plain vanilla conv 2D with 64 and 3 by 3 strides also 2 2 padding same, and input shape is just the same as we gave to generator model. uh, Sorry, input shape in the generator model was 100, but here it's I'm specifying 64 by 64 by 3. Sorry about that. Okay, so and then the next I'm adding a leaky relu and then a dropout so that my model doesn't overfit. And then the next layer is again another conv 2D and then a batch normalization, then another leaky relu dropout, and then the last one is flatten, and then the last is fully connected dense layer uh, and return discriminator. And then I'm getting a discriminator variable with the output of this function. So that's my discriminator model. And now the next step, I have to generate the combined generator and discriminator and compile my GAN model on top of that. So this, sorry, let me get the code of this. Okay, so this is my code for the for combining generator and discriminator together, and then I am compiling it. Discriminator.compile optimizer, I'm using Adam, and because my discriminator will select each image to be either fake or real image, it's a binary classification problem, kind of 0 1. So I'm using loss as binary cross entropy. Then discriminator.trainable, I'm setting false. I will come to that, the meaning and significance of this line in a second. Okay, then I'm compiling the GAN, and if I run the last line is summary, it will create a summary of this compilation, the whole GAN model that I have built. Discriminator is not defined. Okay, I did not run this cell. Yep. So this is the my GAN summary here. Okay. All right. So now the question is why I'm setting discriminator the trainable equal to false. Why would we want to do this is because we are not going to be training the generator model directly. We are going to be combining the generator and the discriminator into a single model, then training that single model. This allows the generator to understand the discriminator so it can update itself more effectively. So setting discriminator.trainable to false will only affect the copy of the discriminator in the combined model, and which is good, because if the copy of the discriminator in the combined model were trainable, it would update itself to be worse at classifying images, which is not what we want. And now the final training. Remember, training GANs is an art form itself because a slight mistake in the hyperparameters and the mode will collapse. So play with different hyperparameters to obtain better results. The overall architecture for our training is as follows. The final architecture of DCGAN here. Number one, initially both the networks are naive and have random weights. The standard process to train a DCGAN network is to first train the discriminator on the batch of samples. To do this, we need fake samples as well as real samples. We already have the real samples, so now we need to generate the fake samples. And then to generate the fake samples, create a latent vector of shape 100. Remember, the first step for DCGAN as per the original paper was a vector, a 100-dimensional vector. So we will create a fake sample with 100-dimensional vector over a uniform distribution, feed this latent vector to the untrained generator network. The generator network will generate fake samples that we use to train our discriminator network. So the training loop begins with generator receiving a random seed as input. Here the random seed means this 100-dimensional vector. That seed is used to produce an image, and then concatenate the real images and the fake images to create a new set of sample images. We also need to create an array of labels, a label 1 for real images and label 0 for fake images. which is the whole purpose of this training, that each real image will be labeled as 1 and each fake image will be labeled as 0. Now, after that, the discriminator is then used to classify real images drawn from the training set and fake images produced by the generator. And the loss is calculated for each of these models. Okay, so that's my... Now let's start with the actual code. I am pasting the whole training code here, and that is this. Let's go line by line over here. So initially, while coding, I'm giving an epochs of 1, but so because I want to see the result almost immediately. But after my coding works perfectly, then I will give an epochs of 300. And why so many epochs I will give is because here the total data set was like 200,000 plus images, but I took only 50,000 of that, and that's why I'm increasing the number of epochs. And batch size I'm using 64. You can also use, of course, 128 to 56 based on the power of your GPU. Then I'm creating two arrays, loss from discriminator model and loss from generator model. This will hold my collect the losses from the discriminator and generator model respectively. With tf.device, I'm using the GPU 0 for, and then I'm starting the looping over the epochs for epochs in range epochs. Print, currently it is just a printing, and then inside each epoch I am looping over the whole range of each batch, because I have to do this training batch by batch, and that's why I'm doing training images.shape 0. That will give me the number of elements in this current batch, or number of rows in this current batch, you can say. And why I'm using these double slashes to divide the batch size, that's because benefits of double division operator over single division operator in Python is that double division returns the float value for both integer and floating point arguments after division. So after these batch size division, I will get the current batch size, and then this is the first step, as we discussed in the previous screen, that the whole process starts with a noise vector of 100 dimension, and my noise shape, this particular variable has already been defined somewhere up here, I think. Noise shape is 100, and I'm using the same variable here. Yeah, so I'm starting a sample, creating a sample, the sample of batch with uniform distribution, and that would be a 100 dimensional vector. And then I am directly bringing in my generator that I defined above to generate a batch of fake images. So this particular line will just pass the noise to the generator model, and predict on batch. With the predict on batch function, it will create a whole batch of fake images from the generator model. Now again, a quick word on how this training code is organized and how we are looping through the batch and epochs. Here we are training two models at once, the discriminator and the generator, and we cannot rely on Keras's .fit function. Instead, we have to manually loop through each epoch and fit the models on batches. And so on the same line, for predicting the image array from the generator, we cannot use a predict function. Rather, we have to use this predict on batch function. And what's the difference between predict and batch and predict function is that predict will go through all the data batch by batch, predicting labels. It thus internally does the splitting in batches and feeding one batch at a time. Predict on batch that I'm using here, on the other hand, assumes that the data you pass in is exactly one batch and thus feeds it to the network. It will not try to split it. So in summary, predict method has extra operations to ensure a collection of batches are processed right, whereas predict on batch is lightweight alternative to predict that should be used on a single batch. So when your when your data set is very large, normally you have to use predict on batch because you want to configure your own batch size and your own way of looping through the data, unless you have a superbly powerful GPU or TPU. So yeah, so this is the logic why I'm using predict on batch. Let's quickly check their documentation here. Predict on batch, yeah. It says returns prediction for a single batch of samples, and it takes input data, the arguments, and input data could be a numpy array or array of list, or a TensorFlow tensor or a list of tensors in case a model has multiple inputs. Okay, and that's what we are passing. We are passing here the noise vector, which is a numpy array. All right, and now after I have generated the fake images, now I am taking the real data set of train images, and that's what I'm doing in this line, that from the whole training images I am getting through the notation of slicing, I'm getting only the images for this batch, that is I into batch size to I plus 1 into batch size. And then I'm creating labels. So first I'm creating some real labels. That is training labels real is will consist of np.1s, because like I said that all the real images will be classified as 1, and that's what this line is doing, creating a one creating all the training labels with classified as 1. And then I'm setting training discriminator.training equal to true, because now I will be training the discriminator, and that's what I'm doing under this line d loss real. Here I'm training the discriminator network on real images and real labels. So I am passing to the discriminator that I have defined above, I am passing a train dataset, which is my real dataset, and train labels real, which is actually classified as 1. So, and what this train on batch is doing, quickly check the documentation. This is runs a single gradient update on a single batch of data. It takes the x as input argument, and which could be a numpy array or a TensorFlow tensor or a dict mapping input names to the corresponding array of tensors. Okay, so all right, now in the next, let me quick, yeah, now I'm training after my after training the discriminator network on real images. Now I have to train on fake images as well, and that's what I'm doing here. First I'm creating some training fake labels, and remember fake will be classified as zeros, and that's what I'm using np.zeros here to create all these zero classified fake labels. And then dloss fake is just the same code like here, but instead of passing real data or real train labels, I am passing the fake images which is generated from the generator model, and also the fake labels, that is this one. And then the noise, it's the same kind of same vector, a 100-dimensional noise vector created from uniform distribution. Okay, and why I'm creating this noise vector here again is because now that my training of the discriminator network is done, now I have to create all the variables to run the training on the whole adversarial network. I will come to that in a moment, but let's first make a comment here so that it's clear. Create to make ready the adversarial network, the whole Okay, so noise vector I'm creating, and then I'm also creating a train label fake for generator training. So these are my these will be fake labels that is classified as ones. That's why I'm creating np.ones. That will be fed to my adversarial network. So, and again, discriminator.trainable I'm setting to false, because like we discussed earlier that when the adversarial network is getting trained, I cannot train discriminator model simultaneously. I have to freeze it. So now the final training part of the generator. To train the generator network, we have to train the adversarial model. And what is my adversarial model? This is the one I'm talking about. So I created this GAN as which is equal to sequential of generator and discriminator both, then compiling discriminator and then freezing discriminator by making it trainable to false, and then compiling this GAN model with optimizer of Adam and loss of binary cross entropy. And this GAN is what I will be using here. Yes. So the generator loss is equal to GAN dot train on batch. Train on batch is again, it will train on each single batch, and to these I'll be passing this noise that I just created of random uniform variable and these fake train labels, which are all classified as one. And why I'm doing this is because, so what basically I'm doing here, that I train the adversarial model on the batch of noise vector and real labels. Here, real labels is a vector with all values equal to 1. And then I'm also training the generator to fool the discriminator network. To do this, I provide it with a vector that all values equal to 1. That is this noise I'm talking about. All these values are equal to 1. In this state, the generator will receive feedback from the generator network and improve itself accordingly. And now finally, I just have to update the loss array that I declared earlier, and that's just these. Loss from discriminator model dot append, I append both the dloss real and dloss fake, and similarly loss from generator model dot append, I append here only the generator loss. And now I manually check, or you can say it's just like a checking, a passive method of checking the images by just looking at them. And that's what I'm doing in these lines of code, is that after every 50 epochs, I'm taking a sample of 10 and predicting from that samples by feeding it to a generator model. And then I'm just plotting those images with plt.subplot function, the fake images indeed. So yeah, so if I run this, I will get fake images. Let's run it. Remember, it's running just for one single epoch, so I will not see any discernible photos or images at all. And that's what it happened, that it ran in 7.1 second, but it was just a single epoch, and it created some images, but those images don't contain pretty much anything, because first of all, it's just single epoch. And then remember, at the very first step, we took only 500 images, so no reasonable training can run on 500 images only. But anyway, it just proved that this code overall is working. And now if I run it for around 50,000 image and for 10-20 epochs, I will start to see the actual images forming, that is fake images forming gradually. And I ran these training code, the whole training code in Colab with 50,000 images and 20 epochs. And then I plotted that result. That is, after this training, I ran this code to plot the images, the resultant fake images that I got from the generator model with this code. It is again a very simple code that we used already earlier in this here. That is, I'm first creating a noise vector and then passing that noise vector to the generator model to predict. And here I can use predict. I do not have to use predict on batch, because it's a small batch and I want to I want Keras to decide the proper way to split the batches. So yeah, so I just passing this noise to this generator model to predict and create fake images, and this then plotting those fake images with the plot.subplot function. It is just simple plotting code here, and I got this kind of result. Um, yeah, they are still in progress. You, of course, do see that none of them are properly recognizable. That's because I did not run the full 300 epochs. I only ran for 20 epochs. So they are kind of still forming at the very beginning stage of forming the images. So yeah, that's my result. And now I am indeed going to run 300. And after 300 epochs, I got pretty believable result. You can run this code in your machine or in Colab for full 300 images, or if you can also for the full data set of 200 plus 200,000 images, and then you get almost the fake images will almost be unrecognizable from the real images. They will be so real. All right, so that kind of wraps up this video. If you like the video, please hit the like button, and also I'll be uploading videos pretty frequently, 2 to 3 times at least per week. So consider subscribing to my channel. Thank you very much.